wind up the morphology. That this is the last section of the book. Um, so we have discussed morphological operations mainly on binary images so far, but they can also be extended to grayscale images also. The definition and other things will slightly change, and they have some applications, so that's why I'm covering it. So grayscale images means now we don't have to have binary image. The the intensity values f, the intensity value fxy will now be, for example, in this profile it can have any values from 0 to 255 or whatever. It won't be a binary image, as well as your binary, as well as your structuring element. Let us say we denote it by b. This also can have a grayscale values. Till now we were considering it only a binary 0 or 1. It would be like a flat structuring element, but now our for grayscale morphology, even our structuring element can be a can take grayscale values and can be of any shape and size. uh, for our discussion we are only going to focus on flat structuring element, but the definition I'll explain that it can have even a non-flat structuring element, because it's more easy to understand flat structuring element. So this is just the profile drawn for this image at this. So as you can see, the values are from 0 to 255. It's not a flat structuring element. So so how does dilation and erosion get interpreted in case of grayscale morphology? So the now we won't have just set theoretical set based set notation. We'll have a more general operation. So for example, the dilation operation in case of grayscale will be defined as like this. It will be over a region or over a small region of B, wherever this structuring element. So a structuring element, if it is a flat or if it's a square or whatever, within that structuring element, um, we will just take, if it is a flat structuring element, we'll just take within that region. We will basically look all the values of f in that region, and wherever the maximum value is, that we will replace it by the maximum value. If it was a flat structuring element, if it was not a flat structuring element, we'll also do, we'll add the value of the structuring element also in this. Before taking the maximum operation, we will consider the fx, the function value at that location plus the structuring element value, and then take a max operation. So for now we'll ignore our values of the structuring element. We'll assume the structuring element is all one flat. So how does a dilation will look like? So let us say our function f has a profile like this, and let us say we have a flat structuring element of some size. So again the dynamics will remain same. We'll slide the structuring element along the function, and at each position here we are within that region, we'll take the maximum value. So for example, if we drop this structuring element, so to interpret it, if we drop this structuring element of some size here, so at this location if you want to see the value, this structuring element will be like this, the region will be like this. So within this region, which is the maximum value of f, it will be the value where it touches. So if you drop the structuring element from top, where it touches that will be the maximum value. So the value at this location will be this value. Similarly, at this location the value will be this, at this location the value will be this, at this location the value will be this, and so on. So in effect, what will happen now, our new image or new function will become, it will be taking a max value. So our function values are going to get increased. So the name dilation uh, can be understood in that way. Basically, it is increasing the, in earlier case we were increasing the size, the values were 0 and 1 only, we were just increasing the size of things. Here instead of increasing the size as such, we are increasing the intensity values locally within a small region. We are just increasing the intensity value of f. uh, so it's something like a max filter here. If the stretching element b is just flat, it's something like a max filter. Take a, we have seen for noise removal max and min filter and median filter. So take a filter and just replace the max value. For erosion we'll do the reverse, we'll take the minimum value in that region. So for taking the minimum value, you basically drop, you push the stretching element from top, from bottom, and wherever it touches, basically that will be the, so these will our new intensity values will be at these locations. So as you can see now, the all the intensity values will go down by doing an erosion operation. Our function values will uh, go, will the intensity values will get reduced. So an example of doing a dilation operation with a flat stretching element on this, it will be this, and if you do erosion, it will, no, sorry, this will be dilation and this will be erosion. So as you can see, when you are doing dilation, the intensity values are getting brighter, and when we are doing dilation, the values are getting darker. So similarly, when we have applied max and min filter, we also got the similar kind of an image. So this is because the stretching element is flat one. The stretching element itself has some other values, the results will be slightly different. So where it will get used, mostly opening and closing gets used for grayscale. How it will get used, we'll explain it. So analogous to the binary morphology, our opening and closing operations will be defined in a similar way. Opening will basically be erosion followed by dilation, and closing will be dilation followed by erosion. The notation of erosion and dilation will be our grayscale thing. So geometrically, if you want to interpret, let us say opening operation, again the geometrical interpretation almost remains the same. We take the stretching element, push it along the boundary from the bottom, and as far as it goes, so for example, we'll take the highest value, achieve it at every point. So take this stretching element and push it from the bottom of the function profile, and at each point we'll take the highest value. So here we'll take this value, this value. So at this point we cannot push it further. So the maximum value here will be this. So effectively what will happen is that this will get cut off. This again, this small uh, this will get cut off again, this. So as you can see, the resulted opening after doing an opening operation will get this curve. You can do it step by step, first do erosion and then dilation, but I'm just showing you the resultant that will happen. The result in effect, what will remove, it will remove small bright details. So bright locations, if the region of that bright location is small, that will get chopped off. So wherever the peak values are, if the peak value was greater than the stretching element, then it won't get chopped off. But wherever the peak of the brightness peak are less than the stretching element size, they will get flattened. They will get basically clipped. So a clipping kind of an effect will happen for a opening operation, and closing operation, it will be all reverse. In closing operation, we'll push the stretching element from above, and at every point we'll take the lowest value. So effectively it will chop off the it will clip off uh, the lower peaks from the bottom. It will clip off the lower peaks from the bottom like this, and the result will be, so it will remove small dark details. So it has some applications. One of the applications that I want to show here, uh, any doubt? What is the intensity profile? Means just at any location, for example, at this along this line, I am just taking this intensity profile because we are going to run the plus slide the stretching element along that column top to bottom like this way. So I'm just taking an example. Let us say any intensity profile along on the path of the stretching element. Let us take any stretching element, any profile, and I'm just showing you the result that will happen. Sorry. We can do that way, but normally the way we run the stretching element is row wise. So we don't run it this way. Normally we slide past it, but if you do it that way also, I think the result will be same. Doesn't matter. If you want to slide it that way, the result should remain same, because anyhow at each location it is going to consider a 2D as per the shape and size. It will consider the entire 2D region. So I am just showing you. That's why this circle is actually representing that this stretching element is a 2D thing. I am showing you just along one dimension, but actually it will be a two-dimensional stretching element. So it will this profile ideally should have been shown in a 2D in two dimension. Then it would have been more. But just for easier visualization and explanation, I'm just taking the one-dimensional profile. And I'm just going to take one or two applications to just show you this thing and where this thing can be useful. So for example, in this image there are some pennies put on the background. Background is quite cluttered, and let us say we want to segment out these pennies. Segmentation we'll discuss more detail later on, but just some sample we are just discussing here. So in this image, let us say we want to segment out these pennies. These pennies have a flat intensity value somewhere in middle, not very low, not very high. Somewhere in between the intensity value is there. You can see at each location. Whereas the background has both peaks as well as uh, dark regions, and there is no consistency. It's all cluttered up. So let me run this program. I'll explain it step by step in the MATLAB. So first I'll read this image. Actually, in fact, it is although it's a grayscale image, but when I looked into it, it was actually a colored image. So converted it to grayscale first. And I want to just show you a 1D profile. So I'm using this function IM profile. So in this function IM profile, I can basically draw the line along which I want to show the intensity values. So as you can see, it looks uniform. The pennies looks very uniform, but actually they are not full top. This is the region of this penny. Okay, and the intensity value is somewhere around 200. in between. The size of this region, the peak size of this region is larger than any of these peaks because the background is all cluttered up. It doesn't has any uniform size. So all these peaks are smaller than this size. So if you take a flat stretching element of this size, I don't know, I can draw it here, but let us say if I take a flat stretching element of this size and do a opening operation, so it is this will survive, and all these things where it cannot go further, it will get clipped off to the stretching element cannot get pushed further, so they will get clipped off to this thing, and only this peak will survive. So if I take this stretching element, so by hand I found out this the size of that was quite somewhere around 6 to 7 pixels. So I'm just taking a stretching element of size 6. I'm doing an IM open operation. So IM open operation is a MATLAB operation for opening. It automatically see whether the intensity and stretching elements are binary values or grayscale values. Accordingly, it does the opening operation. So I don't have to specify I want to do grayscale or not. It automatically does accordingly. And I'll show you the image. Let me just run this section and I'll explain the values. Yeah, this. So this is the I2 figure, which is obtained after doing an IM open operation. I am just scaling it for the visualization purpose. So as you can see, the locations of pennies, they have survived the opening operation. All other locations, they have been clipped off from to to a low values, because as you see in the profile, the stretching element cannot go further away. Only here it will go further. Only in this location it can go further here. All other locations it will be clipped off to some low values. So as you can see, all other regions have intensity values have been reduced. Only the regions around the pennies, the intensity value is little higher. Now it's very easy to segment out these penny regions. What we should do? We should just do a threshold. Earlier, if you would have directly done a threshold, it was not possible. But now we know that the penny regions are exceeding a certain value. All other regions are basically below. So I just choose to manually. I found this threshold is good, and if I apply the threshold value, all the pennies were very easily segmented out. And then I can run a connected component labeling algorithms in image in MATLAB. BW label is a function which actually implements CCL and other things and extract properties for each connected component, limits, area, bounding box, everything. So using the properties, I'm basically drawing the bounding around the bounding box of each connected component label. I'm drawing a red color edge, and this is the result of overlaid on the original image, that those pennies were actually detected properly. And so this is just a very simple application, but very powerful. If without this, to segment it out properly, it will be a very tedious task. Just a simple pre-processing. We'll see segmentation is not an easy task when we discuss segmentation, but this kind of a simple operation can help you in segmentation. This function is creating a stretching element. This is a MATLAB function which creates, you just specify the shape size, and you specify diamond, rectangle. 6 is the size, and disk is the shape. So you specify diamond, rectangle, square, whatever. It will create a stretching element for that. You can manually do it by creating a 2D matrix and all that, but this is a simple utility function. And you specify the size, and I think the last argument maybe tells whether you want it to be a binary flat or not. You can just verify it. And I'm just doing an IM open operation. Open operation, as I said, it is from the profile, it is going to basically serve only this location is survive. All other locations, they are going to get clipped at very low values. So as a result, only these locations will have high values, all other locations will have low values, and you can have a very clear threshold. So that was a result of doing this. Finally, one last operation I'm going to explain here. It's called a top hat transform. It's basically simply doing a opening operation and then subtracting it from the original image f. So it will let me first explain what it will do, and I show the application here. So let us say if you have a function, some arbitrary function with some profile, let us say a 1D profile I'm showing here, which is, if let us say if it has some locations like in the previous case pennies, so some regions around that will have high values and all other regions. In the previous case it was all random, it was all cluttered up. In this case the image that I'm going to show you, it will have something this kind of profile. It has basically some rice, it is an image of rice particles on a background, on a black background. So the background is all almost constant, but it is not uniform, it is, and those wherever those objects are there, they have some small bump of intensity values. So again here our task, we want to basically segment out those rice particles. So we are interested in finding out these locations. So if you do an opening operation is going to basically, if I choose a stretching element of size little bit of size of this size, for example, uh, what it will do, it is going to basically clip off, it is going to clip off the this function from the top. So this thing, so this our uh, our dotted operation, dotted curve will be our open curve. And now if I subtract it from the original image, then I'll be left with, so the opening operation will give us only the background, and if I subtract it from the original image, I'll get back only these bumps, which are basically your objects. So let me show you the example, it will become more clear. So this is the image that I have taken, and the task that I want to do, I want to segment out these rice regions. The problem here, what is the problem? Can we segment out this rice region? If we do a, if we choose a threshold value, why? Like chessboard? Yeah. So the illumination, the background is not constant. It's a, there is a variable illumination here. So I'm just showing you the profile again, the histogram of this image. So the histogram of this image looks something like this. So it's easy to threshold when there are only two peaks and there is a clear value between two peaks. So most of the, so for example, uh, in this case, for example, our price particles are going to have a high intensity values and the background values are going to be low values. So ideally we wanted the rice particle, which is our foreground regions, to be concentrated at one location and the background to be concentrated at another location, and in between would have chosen a threshold value and would have separated us. But now we don't see a single value here, we have two, because of the variable illumination. So if we choose a threshold, let us say somewhere, if you choose a threshold somewhere here, the the image will look like this, the result will be look like this. If we choose a threshold in this valley, we will be missing out this bottom rice values. So it's not, the distribution makes it difficult. We don't, if we could have chosen two threshold values and then some complicated algorithm, we could have done it. But an easier way to do this is, can we eliminate this variable illumination? So how we are going to do that? If I do an opening operation with a distressing element of size 15, here I have taken 15, that roughly responds to the size of the rice region. and I'm doing an IM open operation, and that I'm calling it as a background. Why background? Because after doing an open operation, you will be left with the bumps. The bumps will represent your rise regions. They will be cut off, and you will be only left with the background illumination. So let me show you this background illumination first. So this was the image on which I applied this opening operation with a destructuring element, and this is the output. And as you can see, this output actually represents kind of the background illumination in this image. On the top side there is a brighter illumination, and the bottom there is a darker illumination. So this is giving you the background. This is giving you the background profile now. Now what we can do, if we subtract this background from this image itself, your new image becomes like this. Now what is good thing about this image? The background is now more or less consistent. So if we take a histogram of this image, as expected, all the rise regions, the intensity values are distributed in these bins, and all the background intensity values are distributed in these bins. So now we have a clear value between them, and we can put a threshold somewhere here, and by putting a threshold there, you can very neatly segment out all the rise region. So this is the some application of, so we are calling it top hat transform because we are recovering the top portion of, or the from the top we are taking. Similarly, there is a bottom hat transform where we take the closing operation and then subtract from the, so if we take, if we do this way, it will give a top, it's called bottom hat transform. It will do the reverse thing, and we can think of applications later on. So in the books there are some more applications. Due to time shortage, we will not cover every them in the class. So in summary, we basically discussed morphological processing, and it was mainly used to remove imperfections added during segmentation, and also we have seen it can help us in segmentation. And the basic operations that we just studied were erosion and dilation, and using them we have an opening and closing operations, and with that we could actually perform advanced morphological operations by combining these things suitably. And we also extended this thing to grayscale. So I hope you found this morphological operation interesting.